Welcome to the Deep Dive. Today we're tackling something pretty deep in the weeds of computational physics. Our mission is to take these dense sources and boil them down into what's really happening on the cutting edge of manufacturing.
We are going right into the algorithms that basically predict how metal bends and breaks. We're talking about the mathematical models engineers live and die by when they're designing, anything from a car door to a turbine blade.
Right, and this isn't just theory. This is the code that makes the difference between a process that works and one that costs a fortune in failed attempts.
Exactly. We're focused on what's called plastic deformation, how metals permanently change shape. It's the absolute key to advanced manufacturing.
And the context here is huge. Demand for new, better metal products is constant. The alloys get more complex every year, and companies are just desperate to speed up their development.
Which is where these things called constitutive models, or CMs, come in. You can think of a CM as like the brain of the simulation. It's the software that predicts the final outcome. If that brain is flawed, your multi-million-dollar manufacturing line produces scrap metal.
So our deep dive today centers on a paper that found a major flaw in the standard models and proposed a really clever fix. They're chasing the holy grail of engineering, really.
Oh, absolutely. Perfect accuracy and incredible speed. They've developed a modified elastic plastic model to fix a mathematical problem that's been around for decades.
And the payoff could be huge, right? We're talking about something that's potentially, almost 30 times faster than the current more accurate alternative?
That's the headline number, yeah. A 29-fold speed increase.
Okay, so let's unpack that. Before we get to this brilliant solution, what was the problem? What was this Achilles heel that engineers were dealing with?
Well, the story starts with the classical theories of plasticity. They were okay for describing basic things like creep in metals, but they had a huge blind spot. They couldn't describe the evolving structure of the material itself.
And why is that so important? I mean, if I bend a piece of steel, all I care about is whether it breaks.
Right.
Why do I need to know what the crystals are doing?
Because that's where the properties come from. The final strength, the toughness, it's all determined by that microscopic arrangement of crystals. If your model can't track how that internal structure is changing, you're just guessing at the final result.
I see. So that's what led to these two-level models based on crystal plasticity. Mm-hmm. The big names, right? Taylor, Bishop, and Hill. The TBH models.
Exactly. They introduced internal variables to track what was happening at both the big macro scale and the smaller meso scale. But even those early models had issues. They assumed the material was rigid plastic, which created some mathematical headaches.
A researcher named Lin fixed some of that, I think, by adding in elastic deformation.
He did.
Yeah.
And that was a huge step forward. It got rid of a lot of problems. But one massive flaw remained, and this is the core of our story. The uncertainty in the selection of active slip systems.
Okay, a slip system. Let's give our listeners an analogy. If I picture a crystal as a deck of cards, a slip system is just one of the planes between the cards where they can slide past each other.
That's a perfect analogy. That's exactly it. Plastic deformation is just billions of those little decks of cards sliding on specific planes. And Schmidt's law tells the model when the stress is high enough for a specific plane to start sliding.
So where does the uncertainty come from? Why can't the model just pick the planes that are sliding?
It's a problem of geometry, really. The math that calculates the stress response exists in a five-dimensional space.
Right.
And the limits of that space form a sort of complex shape, a Yale polyhedron.
Like a weird multi-sided die in 5D.
Precisely. And the math only gives you a clean, unique answer when exactly 5 of those sides, which correspond to 5 active slip systems, meet at a single point of vertex.
But I'm guessing real metal doesn't care about the neatness of the math.
Not at all. In something like aluminum, which has a face-centered cubic structure, you can easily get vertices where 6 or even 8 of those slip systems all satisfy the conditions to be active at the exact same time.
And the model just throws its hands up. It has, 8 possible answers, but only 5 slots to put them in?
That's the ambiguity. You have more possible paths than the equations can handle. Historically, people tried workarounds like picking the 5 that used the least energy, but there was no real physical reason for it. It was a patch.
Okay, so the foundational models, the elastic plastic or EP models,
yeah,
were fast, but had this fatal flaw. So where did the field go from there?
They went to the alternative, the elastic viscoplastic models, or EVP. These came about in the 70s. They work differently. They incorporate how fast the material is being deformed, and that inherently gets around the whole ambiguity problem.
So problem solved. The EVP models are the answer.
Well, yes and no. They solved the physics problem, but they created a computational one.
Ah, there's always a trade-off.
Always. See, it's been proven that the EVP models do converge on the correct EP solution. They're physically sound.
Right.
But to get them to converge, you have to make the math stiff. And stiff equations are a nightmare to solve. They require tiny, tiny little time steps in the simulation to stay stable.
So in practical terms, they're just incredibly slow.
Painfully slow. We're talking about simulations that are so costly and time-consuming, they're almost useless for the kind of rapid design work industry needs.
So you have the old, fast EP models that are flawed, or the new, accurate EVP models that are too slow to use?
That's the dilemma, which is what makes the mission of this paper so compelling. They wanted to take the speed of the old EP model but fix its flaw, getting the best of both worlds without the computational trap of the EVP models.
Okay, so let's get into their solution. How did they pull it off? What's the big idea?
The big idea is actually pretty simple in concept. They decided that all slip systems that satisfy the conditions to be active get to be active. No more picking and choosing. They all have, equal rights.
But how does that work mathematically? If the old system broke with more than 5, how does this one handle 8?
They found a basis for it in the mathematics. The space they work in, the space of asymmetric deviators, is actually 8-dimensional. So that suggests that, theoretically, you should be able to handle up to 8 active systems without the math falling apart. It gives them a solid ceiling to work with.
Okay, so they have a theoretical justification. So what's the actual procedure when, say, 7 systems are active at once? How does the calculation work?
It's a really smart, iterative process. When the number of active systems, which they call Ka, is more than 5, they split them into 2 groups.
Let me guess. A group of 5 and then the rest.
Exactly. The first set, D, always has 5 systems in it. They solve for the shear rates in this set using the classic reliable method from the old Lin model. That's the foundation.
Okay, so they start with what they know works.
Right. Then, for the remaining systems in the second set, U, they use a different method based on decomposing the velocity gradient. You can think of it as a refinement step. They take the answer from the first 5 and use it to figure out what the other 2 or 3 must be doing.
And they just keep iterating on that, refining the answer until it all balances out.
They keep iterating until the difference between one step and the next is smaller than a tiny accuracy goal, epsilon. It's a hybrid approach that uses the strong, stable core of the old method to solve the more complex problem posed by the new one.
That does sound elegant. So the big question, did it work? Let's get to the results. How did they test it?
They ran a bunch of numerical experiments, simulating a block of 343 grains of aluminum. They compared their new modified EP model against the slow but accurate EVP model.
And they cranked up the difficulty on the EV model to make it more accurate, right?
Yep, they tested it with a sensitivity exponent, all the way up to 300. The higher the IM, the closer the EVP model gets to the perfect answer, and the stiffer and slower it becomes.
So at the macro level, the big picture stuff an engineer cares about, how did they compare?
The results were excellent. The overall stress predictions, the von Mises stress, were almost identical between the two models, especially at that high M value. The stress curves basically lay right on top of each other.
So for predicting how much force you need to stamp a part, the new model is just as good.
Exactly.
Okay, now for the payoff, the speed. How much faster was it?
This is the mic drop moment of the paper. For a simple tension test with the Rammet at 300, the new modified EP model was 29 times faster.
29? That's not an improvement, that's a revolution. A simulation that takes a full day now takes less than an hour.
It's a total game changer for iterative design. And even for a much more complex test, a 2-step loading path, it was still nearly 16 times faster.
Wow. And that all comes down to the EVP model being stuck with that tiny constant time step.
That's the main reason. It has to crawl along to stay stable. The new EP model can be dynamic, it can take big leaps in time when the deformation is simple, and only slow down for those tricky moments when lots of systems are active. It's just smarter.
So it solves the ambiguity, it's just as accurate on the macro level, and it's insanely fast. This sounds almost too good to be true. There has to be a catch.
There is always a catch, and it is a fascinating one. While the big picture macroscopic results were a perfect match, the analysis of the meso-level variables told a completely different story.
The meso-level. So not the overall strength of the bridge, but the placement of every single rivet.
Perfect analogy. We're talking about the accumulated shear in individual slip systems, the specific orientation of each tiny crystal grain, and on that level, the model showed a huge and growing difference over time.
How is that even possible? If the final bridge is identical, how can the rivets be in different places?
Because the models, over time, were choosing different sets of slip systems to get to the same result. They were taking different microscopic paths to arrive at the same macroscopic destination.
So the final stress state is the same, but the internal texture and history of the material could be completely different.
Fundamentally different. And this is a major scientific insight. That common wisdom that EVP models converge to EP models. It's really only true for the macro level stuff. At the micro level, they can be worlds apart.
Which means the new EP model is a fantastic tool for an engineer who needs to know forming forces, but maybe not for a material scientist who's studying the precise evolution of the material's internal texture.
That's the nuance, exactly. They've created an incredible engineering tool.
So to sum it all up, this modified model finally fixes that decades-old ambiguity problem in the EP framework. It honors all the active slip systems, and the reward is this incredible speed boost.
Up to 29 times faster while keeping the high-level engineering predictions just as accurate. It opens the door to optimization studies that were just computationally impossible before.
Which brings us to a really interesting crossroads and maybe a final thought. Given that this new, much faster model gets the big picture engineering answer right, but gets the microscopic details wrong, how much does that microscopic path really matter?
It's the ultimate question of pragmatism versus purity, isn't it? Should we prioritize computational speed for industrial progress, saving enormous amounts of time and money, or should we insist on microscopic physical accuracy for fundamental science, even if it's 29 times slower? It really forces you to ask, what is the purpose of your simulation? And that's something for you to think about.